Okay, hi everyone. Welcome to What's New with EMR. In this session, we will explore the new features of Amazon EMR. We'll deep dive into certain areas. My name is Neil Mukherjee. I'm part of the EMR PM team. So with that, let's start. Now, maybe a quick poll by show of hands. How many are using EMR in a production environment? Oh, wow, substantial numbers. Great. Well, EMR is where you run big data workloads on open source frameworks, and looks like most of you are familiar with that. So we have the most recent versions of Spark, Flink, Hoodie, Iceberg, Hive, and so on. And we stay up to date with the last 60 days of each release. You have many options to kind of lower costs. So example, reserved instances, savings plan, spot instances, which is spare capacity that AWS makes available to you sometimes at up to 90% discounts. And what is important to note, while you have all of these open source engines, and we have 100% open source compatibility, especially for the core engines like Spark and Presto and Trino and Hive, EMR gives you performance-optimized runtimes, which are up to 3 times faster than the equivalent open source versions. EMR is built for using S3 as storage, and with that decoupled compute storage model, you can scale your compute and storage independently. EMR comes with the MRFS optimized committer that we are constantly improving to give you better functionality over S3, and we'll talk about that in subsequent slides. And while EMR is fully managed, you have multiple options to deploy EMR depending on what is the best fit for your organization. And we'll see more of that in the next slide. So EMR on EC2 gives you the most widest range of an EC2 instance choices. Many customers here are moving to Graviton 2, which is our newest generation of ARM64 processors that give you a cost as well as performance advantage. You get the widest options of engines here. Like we have around 21 options of applications that you can launch an EMR cluster, the most common being Spark, Hive, Presto, and Trino. For organizations who are heavily invested in Kubernetes and use EKS, then we have for them EMR and EKS. That gives you an option to consolidate infrastructure with other workloads. So you can have an EKS cluster that is serving maybe your web services or maybe APIs for some other services as well as EMR. And especially if you already have a Docker CI/CD process, then this model fits in very well. And we'll discuss the optimizations that we have done this year for EMR and EKS. For those of you who want to take advantage of the benefits of EMR but want to keep equipment in an on-premises environment, we have EMR on Outposts. And I'm most excited to talk about our newest offering, which is EMR Serverless, which gives you all of the benefits of EMR without the worry about clusters or servers. So this is a quote from Customer Global. They have been using EMR to power their data mesh processing needs for dozens of teams. They like the autonomy where each team is free to choose the compute resources they need and scale as per the use case. Traditionally, we have seen customers in on-prem have monolithic Hadoop clusters, which are often contending for resources. With EMR, you can launch a cluster in minutes. You can launch multiple clusters in multiple AZs for individual workloads. Each team can get their capacity needs fulfilled independently. Now let's look at a use case. Now this is a workload from a customer, FINRA. And this workload is called CAT. And this workload processes trillions of marketing events every day and then reports errors to firms and exchanges. Now, what is this workload end-to-end has a very aggressive SLA of 4 hours. Let's have a quick look at some of the, read the architecture diagram right to left a bit. And this is common. Many workloads have this pattern where there is the first tier of raw storage, where that's the ingestion storage. They launch an EMR cluster right when they need to process the data. And this is a transient cluster model that is very well suited for EMR that will do the first level of processing and then move data to a second tier. From the second tier of data, they have various consumers. On the top, you have SFTP, where some firms will read it from FTP. On the bottom, there's an S3 bucket, which is served directly to exchanges. And then the next tier of the pipeline begins, where you have multiple other ephemeral clusters launching to do further processing of the data, and then the final data is made available in the data storage bucket at the end, as well as the final catalog at the end. So what's amazing about this workload is the scale. This workload used up to 150,000 EC2 instances per day in this year. And at this scale, one of the most common concerns is to lower costs. How can we lower costs on EMR is probably the most, on Hadoop and Spark, is one of the most common questions that we hear. And the key benefits that you get from EMR is not just saving of support costs. For those in on-prem environments, there's a lot of costs that add up that Hadoop administrators, data platform administrators are very familiar with, like setting up a cluster, setting up Hadoop configuration, cluster tuning. Now, hardware setup is itself a journey where you're doing capacity planning, you're doing procurement of hardware, deploying of the hardware, and finally, even the ongoing maintenance of your data center costs. All of that goes away with EMR. You can launch a cluster in minutes, as many as you want, per workload, per team, and so on. But for those of you already on the cloud, the key benefits of EMR is that with each release, we have chosen the right versions of these open source frameworks readily available for you. The right version of Spark with the right version of Hive and with the right version of Hadoop, and all is packaged for you so you can start using it in minutes. When it's time to upgrade, the bleeding edge version of these frameworks are available to you as well. And if you need help, if you hit a bug, maybe you see the next version of Spark has a performance regression, then you have someone to reach out to. You can reach out to us, and we have your back. We have the expertise. We have built the teams that are dedicated in each of these frameworks, and they can help you. We often work, we always work, actually, with open source communities to make sure that especially for frameworks like Hoodie and Iceberg, where these features are going into the open source frameworks as well. So let's look at some of the cost optimization options that are available in EMR. So the most common being transient clusters. And traditionally, customers have been launching persistent clusters, and there's always the burden of utilization. Is my resources really 100%? Not even 100%. Is my really getting utilized? And the average number of utilization we see for persistent clusters is 40%. So that's a tremendous waste of compute capacity. Hence, transient clusters is a great choice where a cluster launches exactly when it needs to, and when the workload is over, it terminates. That's exactly the model that FINRA uses. The next saving options are obviously savings plan, and in reserved instances where you have some kind of a commitment, and that gives you significant discounts. And then the final one is spot instances. Using spot instances, you get up to 90% discount over on-demand instances. Our largest customers are almost at 100% spot instances in terms of how they use EMR. Instance fleets is actually a great way to use spot instances where you can diversify your EMR cluster requests by saying, give me a diversity of instance types. Give me some of maybe R5 4x, R5 8x, R5 12x, and so on. With that diversity, if you ever have a spot interruption of one kind of instance, EMR will rebalance and can give you more of the other type. Instance fleets are also multi-AZ aware. Now, this is a very common concern. We often say that you should have architectures that are not AZ bound. Now, instance fleets, especially when using ephemeral clusters, are multi-AZ aware in the sense you can select multiple AZs. You can say launch in the right AZ, launch in any one of them, actually, and we will figure out the right AZ based on the capacity pools, which we can monitor. We get real-time capacity insights, and then we can monitor, okay, maybe this AZ is the right depending on the spot instances you have given. Big data workloads are especially well-suited for spot instances, as like Spark, for example. If there's a spot interruption, EC2 gives us a 2-minute warning before taking away an instance. And what EMR has built in is that when we detect that warning, we will mark that this node shouldn't schedule more tasks. And while Spark, if that node goes away, Spark will allocate new tasks to healthier nodes. So there's no interruption to your jobs. In fact, we see less than 5% of workloads are interrupted by spot instances. So highly recommended. Look into using a spot instances or at least a mix of spot and on-demand instances for your workloads. And that can make a significant difference in cost. Now, I've already mentioned EC2 spot instances, but the key point in this is that you don't have to use spot instances just for cost. You can use spot instances for getting additional capacity. As Spark is a distributed processing engine, so are all the others. As you give more capacity, your work gets done faster, and that also lowers costs. And it beats your SLA at the same time. So that is a great advantage. So definitely use a mix of spot and on-demand instances for your workloads, and make those on-demand instances reserved as well. That gives you the maximum value from EMR. Many EMR customers are moving to Graviton 2. Graviton 2 gives you, as per our benchmarks, 12 to 16% improvement in performance, while it is already priced at 20% lower than the corresponding x86 version. So you get a net better price performance of 30%. Now this is a no-brainer. You should definitely be investing, launching Graviton. Now, Graviton being a different architecture, there is a chance that certain libraries will need to be recompiled, but most common libraries that are used nowadays in the Python and Spark world have the ARM64 equivalents available. And last but not the least is elasticity, right? It's a very important cost optimization lever, where managed scaling is available in EMR. This is a managed algorithm that constantly improves and giving you a managed experience of elasticity. It will track high resolution metrics, and while the old auto scaling used to track CloudWatch metrics, that was 5 minutes behind. This tracks real-time, almost near real-time metrics, has a fast reaction time, and can scale up your EMR cluster as per demand, and can scale in when that demand subsides. And the customers have achieved up to 20 to 60% cost improvement by enabling managed scaling. And what makes managed scaling great is that you require very little except to specify the boundaries. Here's the min, here's the max, and the cluster will do the work for you. Now let's look at some of the enhancements in all of these features that we have done this year. One of our top priorities is reduced startup times, especially for ephemeral use cases like Finra has, for example, where they launch a cluster. It is important that the cluster comes up fast, right? Because the startup time is affecting the SLA of your jobs. So what we have done, we have reduced startup times for EC2, EMR on EC2 clusters in a private subnet by up to 30%. Now, most customers are expected to launch clusters in private subnets. It gives you security, of course, and the network isolation that comes from it. Now, this especially works for customers who have task nodes. Now, prior to this, EMR has 3 kinds of nodes: master node, the core group, which has HDFS as well as compute, and the task nodes, which are pure compute. Earlier, we used to launch them sequentially. Master and core used to come at the same time, tasks used to come later, but now we have parallelized operations. All of it really comes up at the same time. That is what gives you the benefit of up to 30% improvement in startup times. We have made managed scaling Spark shuffle aware. So Spark has shuffle data in the nodes, and subsequent stages can actually use it. So what we have done, we have made managed scaling shuffle aware so that the nodes don't scale in if there's shuffle data on those nodes. And when the shuffle data is released by Spark, that's when nodes can start scaling in, and that leads to better performance as well as lower costs. And finally, we have GP3 volumes available. GP3 volumes give you 20% lower price than the prior GP2 volumes. So that is highly recommended. If you're using GP2 volumes today, you can easily move them to GP3. And what it also gives you is that you can scale performance in terms of IOPS and throughput independent of your storage. So that is one additional benefit of GP3 volumes. Now, EMR and EKS has, as I mentioned, has the same runtime as EMR and EC2, so you get the same advantage where Spark runs 3.9x faster, and we'll show the benchmark for it in subsequent slides. Now, this is a common deployment option for organizations who are using EKS and want to consolidate the infrastructure across organizations. You can now have a shared EKS cluster where you have certain limits by teams as well as workloads. You can start jobs quickly, and that's mainly because this is a containerized environment running on EC2 instances. And so unlike EMR and EC2, you can start job in seconds, while it might take minutes in EMR on EC2 there. Now, one more key differentiator here is that while EMR and EC2 is a single AZ cluster, you can have a multi-AZ cluster here. And that takes away the worry of AZ failures, or what should I do if an AZ is impaired, or really what is my AZ disaster recovery strategy, and so on. So EMR and EKS can be a great solution for it. You can still restrict a job to be in a single AZ, so you don't incur any performance or cost penalty of inter-AZ data transfer. But but you're using the capacity of the entire region by having an EKS cluster shared across multiple AZs. And then finally, you have the serverless option with the EMR and EKS if you choose Fargate, AWS Fargate as the underlying layer, instead of EC2 instances. This is a code from a customer Stitch Fix. They use EMR and EKS at scale, and they have migrated from EMR and EKS to open source Spark on Kubernetes. On two fronts, it helped them consolidate. One is multiple Spark versions now coexist on that same EKS cluster, along with other workloads as well. So now you have a shared capacity pool that is being managed, let's say, by your Kubernetes infrastructure team, where EMR, multiple versions of EMR exist along with other workloads. And this led to a 45 to 55% reduction in infrastructure cost. And because of the lack of resource contention, they could reduce job failures up to 25% and out-of-memory errors by 90%. Now, some of the key features that we have built on EMR and EKS this year is we have job templates. So job templates are like your data engineering teams submit jobs, and they often have the same parameters getting repeated. So what you can do with job templates, you can give data engineers a template saying, go fill this template, and when you instantiate this, you will get a job. The template can have common arguments like source data, target location, maybe encryption keys, and arguments like that. Also the benefits that you can enforce certain arguments to be always there. Example, encryption keys. So in a way, you can default some of them, as well you can enforce some of them. So that is so with job templates, this kind of minimizes all of the arguments, parameters that data engineers have to do when you're submitting a job to an EKS cluster. The second one is a Spark SQL runner. Now, This is a very common ask we have seen where your data analysts tell us that, okay, Spark is great, but there's so much code to write, and Spark SQL has come a long way. So why not give us somewhere where you can write SQL scripts? And that will be our pipeline. And so what we have done with the Spark SQL runner is that you can specify your entire pipeline as SQL scripts, and we will instantiate corresponding Spark for you. Now, this can make it very convenient to have large-scale pipelines using just Spark SQL DML. So we have got the latest DynamoDB connector now as in a part of EMR and EKS. This gives you easy access to DynamoDB for the use cases that need it. We have added enhanced job failure messages where now prior to this, error messages from the EKS control plane used to be in EKS. Spark driver error messages are in the Spark driver and so on. So now what we have done, we have made sure that all the error messages are available in one place, that is the Spark driver logs itself, so you can see it. At the same time, they're also available in the described job run API. So for orchestration, let's say Airflow is submitting these jobs, you can get the errors all in one place. Now let's have a look at one of the most important areas that we do a lot of work, which is performance optimized runtimes. As I mentioned, Spark, Presto, Trino, Hive, they have 100% open source compatibility, but we have optimized runtimes. So with each release, we do a benchmark of open source Spark versus EMR Spark. And this is the latest benchmark that we have on Spark 3.30 on EMR 6.9, comparing it to the open source Spark 3.30. And we see a 3.9x faster on total time. This benchmark is done on a benchmark derived from TPCDS 3 terabyte scale. And we have made sure that both sides, both in EMR Spark as well as open source Spark, we do no additional tuning. They both are at default configurations. We do also compare year over year the improvements in EMR Spark. So if you compare what we call reinvent release was EMR 6.5, and then this year's release is EMR 6.9, you see a 30% improvement. It's 1.3x faster. Again, this is the same benchmark. Now, the main takeaway from this is that it is a good idea to always stay up to date with the latest version of EMR. So you get these performance benefits out of the box, and these will directly translate to lower costs as well. If your job runs faster, it can translate to lower costs. And at least 1 or 2 years, it is time to evaluate and move to the next version of EMR. Now let's look at open source Trino compared with the EMR runtime. So this is the same benchmark done with Trino 388 on EMR 6.9 compared with open source Trino. It's up to 3.1x faster on GeoMean and 4.2x faster for the total time of the benchmark. Now let's look at the Hive numbers. Now Hive is still very much used as in the big data world. It's the second most popular engine after Spark on EMR, and customers use Hive at scale. Now Hive works great on HDFS, but when you make it work over S3, certain quirks of S3 makes Hive slower. And so Hive write performance was something that we really wanted to optimize. So the way Hive writes to its underlying storage, it writes to a staging directory, then it'll do file renames to move the files to the final location. Now file renames are just metadata operations on HDFS, so no one barely notices them. But on S3, we don't have file renames, so those are all file copies. So that's what made Hive writes slow on S3. But now we have a feature on EMR 6.7 onwards, which has the 0 rename write. So the EMR Hive committer doesn't do the rename operations anymore, and that improves performance by up to 15 times. And this benchmark was done on TPCX BB 1 terabyte. And yeah, so you have more details. We have a blog post on this. If you want more details on that, you can look it up. And this actually, I mentioned EMR 6.7. It's EMR 6.5. It's Hive 3.12 on EMR 6.5. So let's look at some deeper into some of the engine improvements, and some of which led to this performance improvements as well. So let's look at Presto and Trino first. So what we have added is spot loss handling to Presto and Trino. Presto and Trino are the most popular low latency query engines we see customers use, but they're not meant for an environment where nodes fail. So what happens right now when nodes fail because of spot interruptions, Presto or Trino queries fail, and that leads to a bad end-user experience. Now, those spot failures are not common, but when they do, then your customers will get an error. So what we have done is we have looked into the logic of the spot loss handling. So EMR Studio gives us a 2-minute warning before it takes away a spot instance. We now look at that 2-minute warning and look at the query progression and see, will this query complete in 2 minutes? If it will, we allow it to go ahead. If not, we will fail the query fast and then resubmit the query on healthier nodes, which will make sure that the queries don't fail. So when spot loss ever happens because of a spot interruption, the maximum impact will be that a query will take a little longer. We've also done from EMR 6.8 onwards, we have made multiple plan optimizations that, including improved join reordering, improved join selection, and common sub-expression removal. And this, with these optimizations enabled, you see a 2 times better performance as compared to with this optimization disabled. With EMR 6.9, we have enabled fine-grained lake formation policies. Fine-grained access control is one of the most common asks we are seeing out there. Enterprise customers definitely need fine-grained access control, and lake formation is the AWS way to get it done, and is honored by various services, Athena, Redshift Spectrum, and all, as well as all the engines on EMR, as well as Glue, AWS Glue ETL. And then EMR 6.9 onwards, we also have support for Iceberg and Delta. Now, Project Tardigrade is an effort by the open source community to make Trino handle long-running ETL better. Traditionally, Trino has been mainly used for low latency queries, but now it uses state checkpointing to ensure is when failures happen, queries don't have to start from scratch. And for that, the default is checkpointing in S3. We've added an HDFS for checkpointing as well. So if you have multiple clusters, S3 for checkpointing is indeed recommended. If you have a single cluster, you could use HDFS as well now. So let's look into some of the Hive improvements that we have done. I've already mentioned zero rename. That features out of the box in EMR 6.5 onwards. Another improvement is MSCK optimizations. MSCK repair is the command that is run that registers table partitions in S3 in your Hive Metastore or your Glue catalog. But again, over S3, all of these API calls to do the listing adds in overhead. So we have optimized MSCK repair to do less S3 listing calls. And with that, we see a 15 to 20 times improvement in performance when you do an MSCK repair on large tables over 10,000, with over 10,000 partitions. Parquet modular encryption is now available in EMR Hive. This gives you a granular encryption in addition to all of the benefits Parquet, that is compression, encoding, columnar, predicate pushdown, etc. So fine-grained lake formation policies are now available in EMR Hive from EMR 6.9 onwards. We've incorporated around 300 plus improvements, fixes into EMR Hive. Now these fixes were mostly languishing in open source Hive, where there were PR submitted but not reviewed and so on. We have then made sure we reviewed them, and we merge them into EMR Hive, so those features are available to you. Iceberg support in EMR 6.9 also has been added. So you can now use Hive for your Iceberg tables. Now let's look into the topic of transactional data lakes, a very pertinent topic. Almost every customer is looking into implementing or has already implemented transactional data lakes. So there are two things that make this very important is that we take transactions for granted in the database world, but the data lakes never had it. And now with the frameworks that are evolving in this space, you can have transactions over your data lakes. And the second thing is upserts and deletes at scale. Now, many requirements for that have emerged, especially, the compliance programs like, GDPR expect you to have massive, delete pipelines. Upserts are obviously common where the records coming from source databases might change and you want to upsert individual records ideally, instead of overwriting entire files, which was a norm in the, older days of Spark and Hive. So let's look at a typical use case for a streaming ingestion pipeline and see what are the problems that emerge from, such use cases. So here we have, mobile clients, API clients emitting, let's say, telemetry events, and it goes into some kind of a streaming service. So let's say Kafka. It could be Kinesis as well. And then you have a Spark streaming that reads from Kafka, and then we'll kind of move it to the next tier, which can be a data lake in S3. Now, with such an architecture, some of the challenges which emerges how to make atomic changes, how to make changes to your S3 storage that will, so your readers don't see partial data, they see clean committed data as you're writing to S3, and that's reader-writer isolation problem. How to have high throughput streaming ingestion, and of course the frameworks shouldn't allow this. But with high throughput ingestion, you end up with too many small files, which is an anti-pattern. The smaller files you have, the more is the listing overhead to read the files, to kind of prune the files, and so on. So how do you compact these small files at a certain periodic frequency to larger files? And then sometimes you can have events being restated. Maybe you have a GDPR requirement where you have to delete records. Then the problem becomes row-level upserts and deletes as well. CDC ingestion pipelines have a similar problem where you can have an RDBMS sending you events. DMS, Database Migration Service, is a great service to read those CDC events and then stage them into S3 storage. That's your first tier, which is your raw data. And then there is usually a tier of a Spark streaming, which will read that raw data continuously and merge it into an analytics tier, which is often a denormalized table, and then will sync your Glue catalog or your Hive metastore as well. All of the same problems exist in this space, but we often see that on the target side, you want cluster by secondary keys, or often you need some kind of indexing as well, because while an RDBMS makes it very easy for you to index specific columns, like orders, for example, orders happen by date, but you want the orders by a certain geo, then just go index the geo column and you're done. But in a data lake, you can only organize data in one way. So you want to query by geo, then it'll be a full scan for your table. So now we see if you could cluster by secondary keys, if you could add some kind of an indexing, then that will be a great performance boost. So the three most popular frameworks that have emerged in this space are these, and we're happy to say that EMR 6.9 supports all of that. It supports Hoodie 0.12, Apache Iceberg 0.14.1, as well as OSS Delta 2.10. Okay. Now all of these frameworks, actually, before I go forward, so what is important to note is while these frameworks are kind of evolving, we have been working with the Hoodie community for a couple of years. Iceberg, we kind of announced it last year. OSS Delta is new, and we have added it. And we feel that these three frameworks are aiming towards just similar features, so they're gaining parity with each other. There are differentiators today, and so you as a customer should have a choice on which is the framework that aligns the most with my workload. And hence we have made sure is we are investing in all of them. We have dedicated teams that are working with the corresponding frameworks and building expertise around it. And so if you ever face a problem, maybe a bug that you want fixed, maybe a performance regression, please log AWS support tickets and we can help you there. So let's look at some of the newest features of these frameworks. But actually before that, let's look into the core features that we see makes up the common feature set in this space. So on the ingestion side, you have reader and writer isolation. You have concurrent write support when you have multiple writes happening, where you could have writes happening and maybe you're on the most recent data, while you can have compaction happening, let's say on yesterday's data or last hour's data. Of course, row-level upsets and deletes, which is a core ask, high-throughput streaming ingestion, Flink and Spark support for sure, and sometimes Java as well, automatic compaction of small files, and SQL daemon support. So the last one is especially important is that all of these frameworks, the intent is to eventually make sure they're just SQL. So the choice of choosing one framework or the other is not really change a lot of code, it's just write SQL. So it's not a lot of offer. We think in the long run, it'll be far less effort to switch from one framework to the other as well. Now on the query side, you have the core engines like Spark, Presto, Trino, Flink, Hive support. Of course, everybody wants efficient queries across large number of partitions and files. Incremental query support where downstream pipelines can say, show me what changed in the upstream table. And time travel query support where pipelines or readers can say, show me what changed in this data as your data got abstracted or deleted. Now these come with some administration challenges, which should ideally be automated, where how will you compact files asynchronously in the background? How will you sort and cluster these by secondary keys in the background? How will you clean up files beyond retention period? Let's say you have 1 year or 7 years of retention period. How will you archive data beyond that automatically? So every day, 1 day of data is being archived, and that might be 1 year back. And as commits happen, as transactions happen, how do you have metrics that can keep a track of past commits and rollbacks and such operations? So EMR has Hoodie packaged as part of EMR releases for almost 2 years now. So the latest version of EMR 6.9 includes Hoodie 0.12. Key new features which are quite differentiating is the adding of multimodal indexes, which allows Bloom filter indexes as well as column stats indexing that allows you to do faster lookups as well as does better file pruning. And all of these index building, which kind of detects both for column stats as well as Bloom filters, can be done asynchronously. That's in the background without affecting our writes. So this is a great feature. This year, Hoodie also has announced better schema on read for Spark, and there's only some of the features, but encourage you to go into the latest Hoodie releases and read more on it. Now, Iceberg 0.14.1 is packaged in EMR 6.9. We have announced a Spark 3 support that was late last year, and now with this release, we have Trino, Flink, and Hive support as well. Okay, so the latest version includes time travel support from both Spark SQL and Trino SQL. Iceberg is doing work on the merge and read, and this year, so they have a merge and read support. So merge and read, what it means is that as changes come in, they're written as Delta files and not compact into the final table, and the readers will see a merged view of the changes and the final table so as to get the final snapshot of data. And then after some time, the the Delta files will be compacted into the final table. Now, this feature has existed in Hoodie for a while. Now, Iceberg is also adding this. Optimistic, the concurrency for writes with the glue catalog. Disaster recovery across S3 access points. And finally, Flink and Hive integrations have been added in EMR 6.9. So the customers who already invested into Delta, they asked us to support Delta on EMR with often an intent to reduce costs. And I'm happy to announce that Delta 2.10 is now available in EMR 6.9. We have added engine support for Spark 3 and Trino. You can read more in our Delta docs in EMR. Now let's go into the topic that I am most excited to talk to you about, which is EMR Serverless. Now, how many of you, by show of hands, have tried out EMR Serverless? Okay, so not too many, but I see around probably 10, 12 hands. So it was in 2009 that we launched the first release of EMR. It's been more than a decade working with multiple customers, and we have worked to make EMR the best place to run big data workloads, Spark, Hive, Presto, Flink, etc. And in a way, EMR Serverless is an effort to kind of apply what we have learned from customers working with EMR. If you look at the journey of, rather if you look at the decisions that somebody has to make when they're launching an EMR cluster, what kind of instance types do I want to use? How many of, okay, 3 instance types or 4, how many of them? What should be the size of my cluster? Should I worry about Kerberos in the cluster if I want to keep it secure? Should I launch it in this AZ? How should I have a multi-AZ architecture? Should I worry about OS patching? So all of these problems, what we have done with EMR Serverless, we have simplified it by simply eliminating these problems. So EMR Serverless is, you just make 2 key decisions when you're launching an EMR Serverless application: which release of EMR and which engine do you want to use? Spark, maybe Spark, and 6.9. That's it. And click, you have an EMR application, and then you can start submitting jobs to it. So EMR Serverless automatically scales when the job stages need workers. And so workers are added, and the workers are removed as the demand subsides. You optimize costs through this automatic and fine-grained scaling that EMR Serverless brings to the table. EMR Serverless gives you the same EMR runtime, so you get the performance optimized up to 2 to 3 times faster runtimes. You get the same 100% OSS compatibility, and you get the same benefit of the bleeding edge open source versions available with each EMR release. Multi-AZ is a very common concern. How do you make a multi-AZ architecture within EMR? Customers sometimes have active environments where they have 3 EMR clusters in 3 AZs, but that can lead to low kind of utilization and of course overhead. Sometimes they have an active passive architecture where I have a persistent EMR cluster, and I will keep detecting whether this is up or not, and then I'll launch another one in a second AZ if this is affected. Now, with EMR Serverless, those problems are eliminated. It is multi-AZ, and we'll see more on that in subsequent slides. And the most common orchestration engine nowadays is Apache Airflow. EMR Serverless has integrations with Apache Airflow out of the box. And so if you have an Airflow DAG, it is very easy to kind of modify to make it work on serverless. Okay, so let's look at a quote from customer Malwarebytes. They moved over 50 Hive and Spark workloads to EMR Serverless, and their migration was smooth with minimal source code changes. Of course, it's just Spark and it's just Hive, so you don't have to change any code to move to EMR Serverless. With native integration with the Apache Airflow, they really like that a lot. And they were able to leverage the existing glue catalog as the metastore, which is the norm for most customers on AWS. And finally, they really appreciated that they could launch an EMR serverless application with a few clicks on the EMR Studio console. So it's actually 2 clicks because most of everything is defaulted. It's just 1 click to go into EMR Studio and pick the Spark version, pick the release version, and then go and create your application. So let's look at the main constructs behind EMR serverless. It is jobs, workers, and pre-initialized workers. So once you have an application, you run jobs on that application. And a serverless application can run multiple jobs concurrently. Now, as the jobs run, workers are acquired. As the jobs complete, workers are released. Now, and each job has a per-job execution role. So what this means is that you have multi-tenancy when it comes to sharing the resources of an application. So each job can have a different permission profile. So maybe access different S3 buckets, different DynamoDB tables, Redshift clusters, and so on. Workers are what actually does the work, executes your workload. Like for Spark, it will be drivers and executors. For Hive, it will be test drivers, Hive drivers, and Hive test workers. And workers run the corresponding framework. And while you can run with the defaults, you can change the size of the worker. So example, you know that I need a 4 gigabyte, a 4 CPU, maybe even 30 gigabyte executor for Spark, you can choose it. So you can have fine-grained choices. You're no longer thinking about instance types. You're actually thinking about your workers, which is the more natural way that a Spark data engineer would actually look at the problem. The third feature is in a pre-initialized worker. That's an optional feature. You don't have to use it, but let's say you have a use case where you want jobs to start up fast, okay, within seconds. So what you can have is a warm pool of workers standing by, and when your jobs come in, the jobs start immediately. And then you can also monitor how is my utilization of my pre-initialized workers. Now, if you have more jobs coming in than the pre-initialized workers that you have set up, then those would all spill to on-demand workers. And we'll see kind of more examples on that. So let's look at shared applications with EMR Serverless and what does this mean. So here is an EMR Serverless application. For simplicity, we have kept it in a single AZ, and you have multiple clients submitting jobs. Pipeline B, pipeline A. So one is, let's say, Airflow. One is maybe step functions. Then the third is a data engineer submitting jobs manually, and the fourth is another engineer. All these jobs are kind of coming in. So as these jobs are coming, each of them acquire unique workers, right? Because each one has a different role. They have to acquire unique workers, and they all scale up as per the demands of the stages of each job. Okay, and so this entire EMR serverless application is one capacity pool that is shared by these jobs. Okay, now what does multi-AZ out of the box mean is that in my last example, the entire capacity pool was in a single AZ, but it doesn't need to be. It can be spread across multiple AZs. By default, we actually spread the capacity across 3 AZs. If you set up VPC connectivity, you can decide which AZs, which subnets are actually used behind the scene. And so what this means is that your single EMR cluster application, your EMR serverless application, is a compute pool that is across AZs, and you get 2 benefits from that. One is that you never have to worry about AZ failures, right? Because automatically, if an AZ is impaired, we will submit jobs to the other AZs. And the second is that you can really maximize your capacity of the entire region. Examples for use cases like, as in FINRA earlier, where they had 150,000 instances, getting it off a single AZ can be a struggle. But if you had 3 AZs to pick it from, it will be so much more easier. Now that you can use the capacity of the entire AZ, it's important to have guardrails, right? Because teams, you'll have to have some cost control measures to ensure what your data engineering teams can actually use. And so you can define guardrails saying my EMR serverless application, let it scale what it needs to, but you define the boundary for that scaling, and the maximum boundary setup in this example can be the max CPU is 4,000, which we think is suitable for this team. Now, what you can also do is set up limits for each specific job. For example, job A, and that is something Spark comes with default. You can say job A, use, that's the Spark DRA max executor settings. You can say go scale to maximum 10, right? So maybe job A scales to 10 workers, and job B scales to 20 workers, and job C scales to 15 workers. But the total application, which will serve these 3 jobs, can scale to 4,000 CPUs, right? So you have cost controls built in as well. So let's have a closer look at per job execution role. So with per job execution rule, what you get is that job A has access to, let's say, S3 bucket A, Redshift cluster, as well as CloudWatch log group B, and that's your first set of workers. And your second job has a new set of workers that will access S3 bucket B and DynamoDB table B, right? So that gives you isolation, multi-tenancy in a shared compute pool. We have made debugging jobs very simple, and as a data engineer, what is very important is to be able to get a real-time view of what is my Spark application doing at any point in time. And the best way to have a look at this data is look at the Spark UI, right? It gives you jobs, stages, tasks, executors, the driver logs, executor logs. The entire environment is available to you, and hence this live Spark UI is one click away, one click from the EMR Studio UI for running jobs. Now, how do you monitor jobs that are completed? And for that, Spark comes with the Spark History Server, right? So that Spark History Server is also one click away for completed jobs. And the equivalent for Hive is the Hive Live Tez UI, as well as the persistent Hive Tez UI. So both these options are just one click from the EMR Studio UI. Okay, so that's for Hive, that's for the live, and that's for the persistent one. How about monitoring for capacity, right? I mean, customers use Ganglia on EMR on EC2 clusters. Now, with serverless, common questions are how much capacity am I actually using? Am I really utilizing my pre-initialized capacity well? How many drivers are running? How many executors are running? How many jobs are failing, running successfully, and so on. And so you have all these metrics emitted to CloudWatch every minute, and you have a dashboard so that you can deploy into CloudWatch dashboards to get real-time monitoring of your EMR serverless application. We're very excited to announce that Graviton 2 is an option now. It's when you're launching an EMR serverless application, it's just one click, and you can have an ARM64 Graviton 2 enabled application. Our TPCDS benchmarks showed us that it gives you a 15% improvement in performance. It's already priced at 20% lower cost, so it gives you a net price performance benefit of 35%. Okay, so just a quick recap of all of the core features that we saw today. Graviton 2 support has been added, application capacity insights, as well as job metrics in CloudWatch, live debugging of jobs that are running, and then the history server, that is the persistent server UIs for jobs that are complete, faster, fine-grained auto-scaling, and auto-stop and auto-start. And that's a very important feature, which is not there in EMR and EC2, is that EMR serverless applications can just stop when it is idle, and you can choose the idle time. And when jobs come in, it'll wake up. It's like a pause and resume. EMR EC2 doesn't have it. And so what customers do today is pipelines have to have the cluster orchestration as part of the first step. You no longer need that, because the serverless application has to be defined once and can be used forever. So let's move into interactive notebooks. So for interactive notebooks, which has emerged as a very common use case, most Traditionally, customers used in IDEs for Spark development, but now we are seeing it gravitate towards interactive notebooks. So EMR Studio is fully managed IDE for interactive data analytics. So you get fully managed serverless Jupyter Lab environments, which come integrated with Git repositories of your choice, which can be Bitbucket or Code Commit or Git itself. It is single sign-on enabled, so your data science teams or engineering teams can get a single URL to go into EMR Studio without worrying about all the access that is part of the AWS console. You get the same simplified debugging with Spark and Yarn UI, as I mentioned for EMR Serverless. You get the live UI and the persistent UIs. You can browse, create, or delete EMR clusters. If you want to run notebooks in a headless fashion, we have the APIs for it, and that is very common nowadays to have notebooks as part of your DAGs themselves. And then finally, you can run the interactive notebooks on EMR and EKS as well, in addition to EMR and EC2. Some of the key features is that for single sign-on, we support IAM authentication as well as IAM Identity Center, formerly called AWS SSO. So we have multi-language support in EMR Studio notebooks. This is a differentiating feature because Jupyter doesn't come with this. You can actually have mixed language support. A single notebook can have part of it in Scala and part of it can be in Python. So you can take the advantage of both of these languages. EMR on EC2 clusters also auto-terminate when they're idle, and you can set it up. We support real-time co-authoring of notebooks, which are good for certain use cases. Example, I can invite one of my team members to my workspace, to my notebook, just for some code debugging sessions together, and that can be a great application of this feature. We have a SQL Explorer interface baked into EMR Studio within Jupyter, and that's great for low latency queries, gives you a query editor, gives you a catalog browser, just like Athena in a way, and you get the results, which you can export into CSV if you want. You can mount your local to Studio file system into your EMR cluster, giving you a local development experience. That is something that kind of aligns with what data scientists do today, work on local laptops. So all their local file systems are available to where they have maybe Python packages and so on. Now that is part of how EMR Studio works. And then finally, you have the latest Jupyter Lab, JEG, Levy, and Spark Magic, all of that makes all this magic happen. And we have made sure that we have kept all of that current. You get the latest Jupyter Lab features, which gives you a cell toolbar, gives you a table of contents, and so on. So the folks working on notebooks, you'll really appreciate that. So moving on to the important topic of security, you can think of security in terms of these 5 kind of pillars. Isolation, where your infrastructure is isolated. Authentication, how you identifying users. How your authorization, how you're applying the right authorization rules to the users identified. How do you have the right encryption keys on your data as well as in transit. And then how do you keep a track of who's doing what, which is audit. So for all of them, not going to go into a lot of details here, but that's what it means for EMR. You have isolation in your VPC. For authentication, you have various options, LDAP, and of course Kerberized clusters for EMR and EC2. While for EMR Studio, you get both options for single sign-on. Now, on authorization, you have a cluster level role that you define today. And so all jobs submitted to a cluster have the same permission profile, right? So in a way, it is single tenancy. But now the new feature, which we have enabled this year, is job runtime role, where each job can have a different role, which means a different permission profile on the same EMR cluster. And this concept extends to lake formation as well. That same role can have rules defined in lake formation saying this role can access this table, these columns, and so on. And then the jobs can have those same kind of fine-grained permissions. Encryption at rest and transit is kind of baked out of the box with security configurations. It is very easy. You don't have to go into Hadoop configuration and Spark configuration and all of that. It's just one security configuration. You will define your keys, and you can apply it to the EMR cluster. And finally, for audit, you have multiple options. You have Ranger. If you're having chosen to use Ranger for audit, if you're using Lake Formation, then you can use Lake Formation audit. Okay, so let's have a quick look at multi-tenancy and what it means. So we have two users. User 1 accesses stream 1, bucket 1, table 1. User 2 will access stream 2, bucket 2, table 2. While the same concept for Lake Formation means that these rules are defined in Lake Formation, and you can access certain columns for user 1 and certain other columns for user 2, right? So all of this is now available to you as part of EMR steps. So you can have multiple pipelines, and each pipeline has a separate role, and the roles get mapped into Lake Formation. So now you have multi-tenancy baked into your EMR cluster, okay? And this same concept is also extended to SageMaker Studio for interactive use cases. So a user in SageMaker Studio can specify a Studio execution role, and that is then pushed down to EMR. EMR will use that role in Lake Formation, and based on the rules, each data scientist working on Notebook will have a different permission profile. Okay, so that brings me to the end of my session. Here are some interesting EMR sessions coming up at reInvent. First one is how Disney Plus used EMR Serverless. That sounds exciting. The second one is security. The third one is a workshop on EMR Serverless, which is hands-on. The fourth one is EMR and EKS, if you want to go deeper on that. The fifth one is the FINRA architecture that I spoke about. And the final one is an optimizing hoodie, and if that's of interest. Okay. So with that, I'm going to wind up the session. Thank you all for your time.